Okay, so now I want to show that the Fourier transform of an even function is real valued, and now what can be said about an odd function. Okay, so let's just do this. So let f be even, that is f of minus x equals f of x. Okay, then let's just compute the Fourier transform. F hat of omega is equal wow, okay. Now we're going to have f of x e to the minus I omega x dx. Okay, let's just see if that looks like what I want it to look like. Okay, so we want to show that it's real valued. So there's a number of ways that we can do this. One of the ways that we can do, so we're assuming that, okay, it's an even function that's real valued. Okay, I didn't know if I'd put the explicit assumption that it is real valued. So I have a real valued function and it's even. We want to show the Fourier transform is, we want to show that the Fourier transform is real. So like I said, there's a number of ways that we can do this. I think one of the easiest ways is to show that it's equal to its complex conjugate. If you have a real number that's equal to its complex conjugate, that means it's real. A similar thing is the following. I just thought of, because I think this one will be a little better for us to use for the question about the odd function, and that is, note that the real part, complex number, is z plus overline. That'll give us a bar over 2. Because if z is a plus bi, z bar is a minus bi, a plus bi plus a minus bi, the bi's cancel and you have 2a, and divided by 2 just gives you a. And there's a similar statement if you do minus and put 2i, that gives you the imaginary part. Okay, but we'll do that part in a second. So we'll put a 2 here. Okay, so I think what I'm going to do is compute the complex conjugate of f hat. Oops. Okay. Okay, so we're going to have, I'm just going to copy some of this stuff here. So I'm going to put, so I'm going to do a complex conjugate of this whole thing here. This gives us a complex conjugate here, like this, and like this. We're going to look at it to see what we have. And the complex conjugate of the integral, that's just equal to the integral of the complex conjugate. So we can put the complex conjugate on the inside of the integral. And the reason that's true is if you think about this in terms of a definition via Riemann integrals, that's a sum, and the conjugate of the sum is the sum of the conjugate. That's a little bit easier to see. And then the limit, you get this. So I'm going to make this on multiple lines. I don't know if there's a better way to do this. This is just kind of what is coming to me as I think about it. By the way, like in the comments or anything like that, if you find like a better way to do some of these solutions, or you think you think you might have a better way to do some of these solutions, please let me know. I just kind of think about the first thing that comes in my mind sometimes. That's one of the things I like about this video, is I get to share my thought process with you. And oftentimes, like when I write the notes, for example, I don't do it like this. I don't just put the first thing that comes to my mind. I spend a lot more time thinking about it, but not so much for these. Okay, so let's see what we have here. Okay, now we have the complex conjugate of e to the minus I omega x. Now, what that's going to be, if we have a complex conjugate, that always just involves wherever you see an I, you're going to multiply it by minus 1. So the complex conjugate of e to the minus I omega x is just e to the I omega x. And so this is the following. So I can have the complex conjugate there. We're going to take that away. And so we're going to have this. Okay. Okay, now what I think I want to do, okay, I need to somehow use the fact that it's even, of course. What I want to do, yeah, okay, so what I want to do now, I want that to be a minus sign still. So I'm going to make it a minus sign, but I have to like multiply by minus 1 twice, multiply and divide by minus 1, however you want to think about it. So I'm going to balance it out by multiplying the x by minus 1. Okay. Now, set u is equal to minus x. Then du equals minus dx. Okay, so I'm going to have this, and we're going to continue. Okay, now what's going to happen? The x there, that's going to be a minus u, because x is equal to minus u. That's going to be a u there. The limits are going to get swapped, going from plus infinity to minus infinity, but du is equal to minus dx, so those cancel out. And then what we get is going to be the integral u equals minus infinity to plus infinity f of minus u, and then it's going to be e to the minus I omega u du. And again, the limits should go from infinity to minus infinity, and that should be a minus du instead of du, but the minus from that causes the limits of the integral to be flipped. And we have this. But now, since f is even, this is since f is even, f of minus u is equal to f of u. So we're going to have this, and then this, f of u, which is equal to this. Okay, so what we've shown then is that the complex conjugate of f is, the complex conjugate of the Fourier transform is equal to the Fourier transform. So if you have a number that's equal to its complex conjugate, the only way that can happen is if the number is real. Okay. So I think probably, you know what, I'm just gonna, let's see. This works for the even thing. Oops, what did I do wrong here? So I think I'm gonna rearrange this a little bit. Alright. So we will show that whoops. Come on, dude. we will show that the Fourier the complex conjugate of the Fourier transform equals just the Fourier transform. Okay. Indeed, the complex conjugate. So let's see how that looks now. What did I do here? Undefined control sequence. What? What did it? Oh, something's wrong there. Okay. Oh, come on. Oh, forgot it there too. Okay, so we will show that this, indeed, the complex conjugate of f hat is this. We can bring it all the way down to there. Then we have that. Since f is even, this is that. Okay. Then I'll just say here, as desired. Now, the sort of corresponding statement, so what we want to show then, what the prediction should be, is that if f is odd, then its Fourier transform is pure imaginary. So notice that if you multiply a complex number by I, the real and imaginary parts change, because if you have a plus ib, you multiply it by I, it becomes minus b plus ia. So then what we want to do is we want to show, we're not going to show this, I'm just going to say this. If z is a complex number, then it is pure imaginary if iz is real. Okay, so if z is a complex number, it is pure imaginary if and only if. So it's a pure imaginary number if and only if iz is real. Sorry, if a non-zero. If z is a non-zero. If z is a non-zero complex number, then it is pure imaginary if and only if I times z is real. So let's think about this. A plus ib, you multiply that by I, you get minus b plus ia. Okay, if z is pure imaginary, that means that a is equal to 0 and b is not equal to 0. So then if you have a complex number where a is equal to 0 and b is not equal to 0, and you multiply that by I, it just becomes minus b. Okay, and if I times the complex number is minus b, that means that the real part is equal to 0. Okay, so we want to show that I times z is real. So now what we're going to do, I'm going to copy and paste a lot here. So we will show that we will show that this is real by showing it is equal to its conjugate. Okay, so as above, so there's another way to do this that I will mention in a little bit. So I'm just going to copy and paste a whole lot of this, and we're going to see how far that's going to take me, and hope I don't make a mistake. Okay. All right. So first, actually, we're just going to start here. Okay. Okay, the complex conjugate of I times that is going to be equal to that. And I have the overline here, so I'm going to put the I there. All right. Now I'm going to point out something. So if you have if you have two complex numbers, z and w, the complex conjugate of z times w is z bar times w bar. Okay, so now let me just, oh no, what's the problem here? Oh no, now it doesn't know. What have I done? Hold on. I think that just doesn't belong there, right? Okay, so now we're down here. Okay, so the complex conjugate, we have the i's under the complex conjugate there. The complex, if you have z times w, so zw with a bar on top, so the complex conjugate of z times w is equal to the complex conjugate of z times the complex conjugate of w. So the complex conjugate of I is minus I. So down on this line right here, I've got it kind of moved in here. I'm going to put a minus I. Minus I. Okay, so that's good. Now I have the complex conjugate here. Now if I come down, it's going to be the same computation. So I'm going to have a minus I there. And the complex conjugate makes that positive. When I come down here, it's going to be something similar. Minus I like this. Let's see how that looks. Okay, that's right. Okay, so now what we're going to do, set u is equal to minus x, then du is equal to minus dx. And the above is, I forgot an equal sign here, didn't I? Okay. And the above is, so over line times that. This is equal to, oh, that's nice. I just kind of stopped writing the 1 over the square root of 2 pi. So hold on a second. Let me fix that. So now I'm fixing some problems from above because if you see up here, I forgot the 1 over the square root of 2 pi, which unfortunately I do often. Okay, so now where am I down here? Okay, so now I need to put, and the above is, let me put an equal sign here. Okay, and there's going to be a minus I here. Okay, now what's going to happen, since f is odd, f of minus u is equal to minus f of u. Since f is even, this should say odd. That is f of minus u equals minus f of u. This is okay. This is going to be, oh man, I forgot that 1 over the square root of 2 pi here. Okay, so I'm going to have this. I'm going to have this, but now f of minus u is equal to minus f of u. So the minus sign is going to come out and cancel with that minus sign, and that is equal to this. Okay, all right. So again, what we have, we're showing that the complex conjugate of I f hat is equal to I f hat. So we do this computation, we come down, we get this. Now we do a change of variables, and we have f of minus u. That's what we have here. But since f is odd, f of minus u is equal to minus f of u. So this f of minus u is minus f of u. The minus comes out and cancels with that minus sign, and so we just have this. But this is just I times the Fourier transform of f, and that's what we wanted. Okay, so now we've proven this. I'm going to mention here another method. Note that e to the minus I omega x is equal to cosine of omega x plus I sine omega x. Now use the even odd property of cosine and sine. Yeah. Okay. So that's it. Okay. Very good. All right.